Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's take a look at our homework for 5.2.6. This is part 1, so we're going to only do problems 83 through 87 today. We're going to do 88 through 92 tomorrow. So let's take a look and see what we've got here. Darnell designed a spinner at the right for a game. It still has one incomplete section. Help them figure out the probability of selecting a card on any turn. Show how you got your answer. All right, so what do we have here? We know that this entire spinner represents 100% of the total, and this represents 1/4, this represents 5/12, so the rest of it has to be whatever you would add to 1/4 and 5/12 to give you one answer. So that's how we set up these ratios here. 1/4 plus 5/12 plus the unknown section has to equal 1. And since we've got a common denominator here, we could have 12 as our common denominator. We would rewrite this as 1/4 is going to be 3 over 12 plus 5 over 12 plus an unknown number of 12s will give us 12 12s. So this unknown number here, this is 8, and 8 plus 4 is 12, must be 4 out of 12, and so we'll simplify that down to 1/3. And that does kind of look like 1/3, right? It may not be perfect. Remember, I told you in a previous problem that CPM likes to make these, so they're not perfect, so you don't guess accidentally and get the right answer. What is the probability that on any turn you will not spin again? So if this is the spin again, which is 1/4, the not spin again must be the complement, which is 3/4. And then which is more likely, to lose a turn or to select a card? So if you lose a turn, that's 5/12. If you select a card, that is 1/3. So how do those two compare? Well, 5/12 is actually greater than 1/3 or 4/12. So you're more likely to lose a turn. And that actually, someone could guess this because that looks bigger than this section. So you might be able to figure that out without doing any of the math. But we absolutely want you to show your work to justify your answers. All right, so this is something that we haven't seen in a little while, being able to find the area of different compound or complex shapes. So looking at these shapes, you need to really break them down into their different parts. So we do have formulas for trapezoids, formulas for squares, formulas for parallelograms and triangles. Turns out the parallelogram formula is pretty much the same as any rectangle formula. So you just have to identify the base and the heights of each of these and then solve them and put them together. So for instance, 2.5 times 2.5 is 6.25. That's going to be the number of square units to fill up this square. This trapezoid, we're going to have to figure this out and do a little bit more work. So we know that's 2.5. That's 5. So the total sum is 7.5. And then height would be 2. And the formula says take 1/2 of the sum of these times the height. So what I'm going to do is use commutative property, and I'm going to take 1/2 of 2, which is 1, which means that our area of this trapezoid has to be 7.5 square centimeters. Add those together, that's how you get your 13.75 square centimeters. Here, if we knew the distance from here to here for sure, we could just use the trapezoid formula. But if I'm not convinced that this is an equilateral, I think this might be, but yeah, we might be able to say that this is 5, right? Because if that's 2.5 and that's 2.5, then that would be 5. I'm going to check that out and see if that ends up working. So instead of finding the area of the triangle and the area of the parallelogram and then adding those together, oh wait, I don't know the distance from here to here. It looks like it might be 2, but I don't know if it's 2 for certain, so I'm not going to go there. I'm just going to go ahead and break this down into its parts. So we're going to take 1/2 times 2.2 times 2.5, which is 1.1 times 2.5. And what is 11 times 25? 2.5 times 1.1 is 2.75. Okay, so we know we've got a 2.75, and then this parallelogram has a base that is 2.5 and a height that is 2. I think the most common mistake would be people multiplying 2.5 times 2.5, but this is not a square. That is not the height of this parallelogram. This is the height of the parallelogram. So if we double 2.5, we get 5. Then when we add them together, that's your 7.75 square centimeters. All right, Rachel's collecting donations for the local animal shelter. So far, she has collected $245, which is 70% of what she hopes to collect. So if you recall, we had a percent proportion where we said we always take the part over the total, and that's going to be equal to the percent out of 100. We can take this information here and decide where it goes in our proportion and then solve the proportion. So we have to decide whether or not this $245 represents the part or the total. And that's where reading comprehension comes into play. It says, so far she has $245. So that implies that she's not done. And it also says, which is 70%. So this does not represent 100% of the total. It represents 70%. So that's how we know that this has to be our part. And then the percent is always very simple. The percent always goes above the 100. So now that we've got our percent proportion set up, now we can solve it. And if you can find a giant one, what would you multiply times 70 to give you 245? You can do that. 245 divided by 70 is 3.5. So when you multiply 100 times 3.5, that's going to give you your answer. If you did not realize that you could multiply times a giant one, then you could have always, or maybe you didn't want to because it wasn't obvious to you, then you could just cross multiply and you get 70 times your unknown quantity, which I wrote as n, is equal to 245 times 100, which is 24,500. And when you divide this by 70, you are going to get the same answer. Use your calculators, they are your friend, but the calculator can't tell you what numbers to multiply and what numbers to divide by. So we need to make sure that we understand the basics of how to take information from a percent problem and plug it into the percent proportion. Here's another situation that involves proportional reasoning. Darnell is designing a new game. He will have 110 different colored blocks in a bag. Okay, so that is telling us what the total is. He's going to have this number in the bag, so that's going to be our total down here. Here we've got our prizes, right? If you pull out randomly a blue block, you get a small toy. A purple block, you get a hat, and a green block, you get a large stuffed animal. So it says here, if he wants to have a 60% probability of getting the small toy, then how many blue blocks would you need to have there? So we know that we're going to put a percent of 60, and the part is going to represent the number of blue blocks out of 110 that are in the bag. Here we have 10%. So same thing. What number out of 110 represents 10% of the total? When solving these, you do the same thing that we did over here. You could do cross multiplying, or you can use the giant one to figure it out. And what some students might do is this. They might decide that, what do you multiply times 100 to give you 110? I'm not really sure. But if you simplify this fraction, instead of 60 out of 100, call it 6 out of 10. Now it's a little bit easier to, Now it's a little bit easier to identify what your giant one is going to be, because we know that when you multiply 10 times 11, you get 110. So 6 times 11 is 66, and 1 times 11 will give you 11. And now for some fraction problems. When you're adding fractions together, you need common denominators. So the first thing I would do for these problems is rewrite them so that they have common denominators. So for instance, 1 1/2, if I change that to 1 4/8, now I can add it to 2 1/8 and just add the fraction parts together, add the whole number parts together, and we get our final answer. Here, looks like 30 might be our common denominator, since 5 times 6 is 30 and 3 times 10 is 30. So let's just go with 30 as our common denominator. So let's think of our giant ones. What would you multiply times 6 to give you 30? No. What would you multiply times 5? You would multiply 6. So 4 times 6 is 24. Multiply 10 times 3 to get 30. So 10 times 2 is 20. And then 5 times 6 is 30. So 5 times 1 is 5. Now we're just going to go straight across the numerator. 24 minus 20 is 4. And 4 plus 5 is 9. Now 9 over 30 is the answer, but it's not in simplest form. So you'd want to simplify it down to 3 over 10. Last problem is a little bit trickier because when you set this problem up, 5 3/5 minus 1 4/5, your job is to take 4/5 away from 3/5, but you don't have enough fifths there to take away 4/5, so you have to borrow from the neighbor. Now, the most common mistake I see from students, and sometimes, honestly, I don't think it's a mistake. Sometimes I think students just don't want to be bothered by it and are willing to get the wrong answer by just saying, well, I'm just going to take 5 minus 1 is 4, and 4 minus 3 is 1, and make that my answer, even though they know it's not the right process. Well, if you want to get good grades and you want to understand how all of this works, you have to be willing to put in the time. And it's not that much work, really. Now, I'm going to show you a model to help illustrate this point here of what you need to do in order to solve this problem. If I start off, if I start off with 1, 2, 3, 4, 5 circles, that represents the 5, plus another, that is terrible. Hold on for a second. I got to do a better job. Let's slow down. Rushing is never good. So if I take this one and I break it up into 5 equal parts, and then I only want 3 of those 5 equal parts, I'm going to erase away 2 of those fifths. So this is a model that represents 5 and 1 2 3/5. Perfectly drawn. Okay, now I'm going to take away 1 4/5, but I don't have 4/5 to take away. So I'm going to have to borrow from this one and turn that into 5/5. So that's like me taking the 5, making it a 4, and then adding 5/5 here. So what do I really have here? I really have 4 and 8/5. I haven't changed the total. It's still 5 3/5. I've just rewritten the fraction and the whole number part so that now I can take away 4/5. So let's do that. Let's take away these 3/5 plus another 4/5. And what does that leave me with? It leaves me with 4/5 plus, oh, I never took away the 1, did I? Let's take away the 1 as well because I had to take away 1 4/5. And that leaves me with 4 minus 1 is equal to 3. So that is the process for subtraction with mixed numbers when you've got to borrow from the whole number. And this is an explanation or a visual model to explain why we do what we do. And that ends our homework for today. All right, let's move on to the next activity. Ooh, what am I doing? I got to do this. I got to stop.
Hey, feeling good, like I should. When in Durga,